Nice to meet you, everyone. I'm the first author and the presenter Boseong Jeon from Seoul National University. So today, I'm going to talk about our work, integrated motion planner for real-time aerial videography with a small drone. So here you can find the snapshot of our experiment. So from now on, I'm going to proceed based on these contents. So first things first, so what is this paper about? And this work is devoted to the automation of aerial videography. So for the decades, we have been observing a growing market of commercial drones for various purposes, among which the cinematic application is one of the most widely used fields. So as can be seen in this video, several commercial drones are already capable of tracking a target autonomously without manual operation. However, it seems still challenging to extend the capability toward a cluttered environment, and as can be seen in this video, the actor is being uploaded due to the presence of obstacles. So for the full automation, as we see, the 5 technical issues should be handled in an integrated manner. So first, the flight should be input efficient. Second, the drone should not collide with obstacles. And third, we should ensure the target is visible from camera drone. And fourth, we should balance between two conflicting aspects: quality of trajectory and speed of contagion. And last but not the least, we should ensure our prediction is reliable under the presence of obstacles. And as a side note, we do not assume the shape of obstacles. Then, let us look at briefly several related works to resolve those issues. So the point is that our work can handle all the 5 considerations without any without assumption of the shape of obstacles. So from this capability, we can drive our contribution as stated in this slide. So in this work, we plug in a motion prediction module and complete an onboard integration for real drones. And now we are ready to discuss the details on how to achieve the mentioned objectives in a set of assumptions. So for the convenience, we assume that the map is available in the form of locked map and its distance field also. And next, we also assume that the actor of interest will pass through sparse waypoints one by one, as noted in these green balls. And for example, we can consider the drones which is deployed to sports events such as skiing or a marathon. Putting things all together, we are to compose the following onboard system for autonomous drone cinematographer. So based on the prior information, we first localize a target with a dedicated vision sensor, and we predict over a short horizon, and this forecast is fed into our planning module, and finally the controller operates to track the planning output. Now we step into the prediction module. So the aim of this chapter is to predict a target movement prediction over a horizon with a reflection of the obstacles. And before that, we clarify several assumptions, and the actor will increase its own safety along with its motion efficiency. Also, as mentioned, it will visit a sequence of sparse waypoints one by one. So on top of the assumptions and observations tag denoted as XP here, we forecast the actor based on this optimization. So for the variables representing the prediction trajectory psi, which is ordered set of Z, so we solve it so that it can minimize the observation error and a deviation between the goal G along with the second order derivatives. And additionally, so we have the distance field here, and using this field, we maximize the value of the field which is included in the third term. These objectives can be forwarded into the standard form of covariant optimization with stable convergency as explored in the fifth reference. And we attached here a prediction example where the target is known to travel from G1 to G4. And as can be discovered, the prediction over a horizon was generated, avoiding obstacles and heading toward the goal based on the observations. Then, how are we going to compose the receding horizon planner in response to the prediction, which is introduced just before? So here, I wrote the things we want to ensure for our system as blue boxes, A1 to A4. So you can match the satisfaction level of each component in the first line and how the manner how they are handled in the second line. So rather than putting all of them into one optimization, we decompose the pipeline into this hierarchy. The first, pre-planning, second, smooth planning, in order to balance between two conflicting aspects. So this is overview of our planner, and as we have been talking, the prediction is assumed to be given, and the next step is where the two planners come in. So the former planner is kind of sketching the corridors, so as depicted as a cyan color by means of graph search in reduced domain. And next, the subsequent planner finalizes a smooth trajectory, so in the form of piecewise polynomial using QP. So in the first planner, the generated corridors is to ensure the safety, visibility, and travel efficiency. And it has the three following properties. So first, it will optimize the total travel length along with the visibility, and it will strictly guarantee the safety over the entire corridors, and it will also strictly guarantee the visibility at the skeleton points here. And the next planner takes over the job from chasing corridors, and please look at this red curve. And by inheriting the properties of chasing corridors, it fast computes a trajectory which minimizes the higher order directives in order to ensure the travel efficiency of chasing drones. So we are all set with the building block, prediction, and planners. So now we present the key validation results. So here, we first mentioned the hardware used as camera drone and the virtual actor. The drone has the following as its components, and it brought Onboard. So it runs the visual odometry and target detection and target prediction and planning and the controller. So all things together. And next, regarding the target, we used the Turbo 3 waffle, and on top of which we mounted a green disc for edge detection. So the target is operated by a human, and it will visit two goals, and so they are visualized as magenta region here. And this is video. The target is detected in this red circle, and it is predicted like this. And you can find the chasing corridors and the smooth trajectory inside of it. And the drone here detours to maintain its visibility against these obstacles. So this is the final result of our experiment. Here I also plotted the entire flight history with a view vector toward the target. And also as a supplementary, this slide shows this server simulation results. So we have also tested our algorithm in various environments with several different target movements. So yeah, that's all from me. So if you are interested in my C++ implementation, please visit my GitHub. And thank you for listening and stay well. Thank you.